You know what, these molecules here are glucose molecules, and these glucose molecules are linked together by the COC linkage here. And so wood is just made up of sugar. However, you know, if you try to ferment sugar, this type of sugar, cellulose, you end up with methanol, you know, versus if you just ferment regular sugar. And the difference is this. It's the way it's linked three-dimensionally. It's the shape. So take a look at cellulose. And do you know how sugar is stored in the body? It's stored as glycogen. And what's glycogen? Well, if you look at glycogen, it's glucose linked together with other glucose. These are all glucose molecules, and it's a COC link. And so if you look at cellulose, which is wood and paper, and compare it to glycogen, which is what our bodies use for sugar, they look the same, don't they? And glycogen and cellulose, let's compare it to here. Cellulose versus glycogen. Actually, a bit better to get this comparison slide. Glycogen versus cellulose. And so basically they're made up of the same. They have the glycogen and cellulose have the same formula. And they have the same formula, and they look like they have identical structures, but they're different. You know, and the way they're different is you have to look at the COC link. Do you see a difference? The only difference is how the COC link is. And if you look at this COC link versus that COC link, what's the difference? You know, it doesn't look any different, but there's a difference in how they're linked together. And based on how they're linked together, I mean, everything's the same. It's just how things are spatially arranged in three-dimensional space. And so we have things that are enzymes in our body, and our enzymes are very specific. You know, it depends on the shape. It depends on where the atoms are in three-dimensional space. So with an enzyme, you know, we have enzymes that can digest glycogen, but we don't have enzymes that can digest cellulose. Whereas termites, you know, when termites eat wood, it's like eating sugar. And so when termites eat wood, they have an enzyme that can digest this, that can break this link, but it can't break this link. And so it's just a difference in the three-dimensional arrangement of the bonds. That's all it is. But otherwise, it's exactly the same. You know, glucose molecules linked together. And so this three-dimensional shape is very important. It's very important in drugs. You know, for example, when you make things, sometimes you can't control how they're linked together. So something like ibuprofen has two different ways of linking things together in the structure. And so it turns out like half the ibuprofen you eat doesn't do anything. The other half does. And so like 50% is wasted. So if you make a ton of ibuprofen, half a ton is active, the other half ton is inactive. And so the other half ton is just a waste. Because it's hard to do. It's hard to, because normally when the bonds form, they form randomly. There's some collision and they form randomly. And so that's a big topic. If you can develop, and people are working at this, you know, they're trying, and they're successful for certain things, they can do it. And so what it is it's selective synthesis, where they can synthesize one form and not the other. It's like this, you know, if this were totally random, you know, this is produced in the body, this is produced by the trees or whatever, and when they produce it, it's very specific because they have proteins and whatever else that do this. But if this were totally random, let's say, half your sugar is sugar and the other half is wood, and so you eat that, well, the wood might be good because it's fiber. It might help your digestion, but, it's the same type of thing. It's like that. So that's a big topic. It's a huge topic in biochemistry and chemistry, is how to synthesize these to have the correct, spatial arrangement of the bond. And so the first thing we're going to look at is just using, the quantum mechanics light theory to figure out the structure of these. Three-dimensional structure is really important. And people try to visualize this all the time. So there's, quantum mechanics will help you visualize the structure. See if we can load this up. Here. Okay. Alright. Problems with this. Okay, so that's the second part of this chapter, the shape. And so we can get an idea of the shape using this. Oh, actually, I forgot to talk about hybrid structures. Look at electron pair geometry. Electron pair geometry is not really an accurate use of the word pair. A pair can be anything. It's just a group of electrons. So it could be a single electron up to a triple bond. You call the pair. So valence shell electron pair repulsion theory, or VSEPR. So this is very common. Chemists, if you say VSEPR, they'll know what you're talking about. And all this says is that the shape of the molecule is dictated by electron-electron repulsions. Groups of electrons repel each other, and the shapes will be dictated by those repulsions. So let's skip that. And so if we have two groups, again, a pair is not accurate. Just two groups. And so, well, what's shown here is two single bonds. Yeah, if we have two single bonds, they're going to try to repel each other. And that is, make the maximum distance between them. So if they're 180 apart, then that's going to be minimizing the repulsions there. But it need not be single bonds. It could be, for example, a double bond and a single bond. A double bond and a single bond will want to be 180 apart as well. A triple bond and a single bond will want to be 180 apart. If we have three groups of electrons, then the best way to arrange them is this. This is what we call trigonal planar arrangement, or trigonal planar EPG. EPG standing for electron pair geometry. This one will be called linear. This is trigonal planar. In trigonal planar, we can maximize the distance by arranging them 120 apart from each other within the plane, like this. Again, this need not all be single bonds. What's shown here are single bonds, but we could have a double and two singles, which is very common. Or maybe even two doubles and a single. But three singles is common as well. Now, if we have a fourth group, then the fourth group we put maybe on the top, which pushes these three down. It's going to push them down evenly. So if we put one on the top that pushes these three down, well, it turns out this thing has what we call tetrahedral geometry, or tetrahedral EPG, electron pair geometry. The tetrahedral EPG, all the angles are 109.5. And so no matter what two sticks you choose, like for example this stick and this stick, that angle is 109.5, is tetrahedral. And so it has like a ball-shaped symmetry, spherical symmetry. this is showing it, representing the groups of electrons with balloons. So actually, what would be the biggest balloon? Like a single bond, a double bond, a triple bond? What would be a bigger balloon? Well, this could be like two single bonds. Right? So if I make a double and a single, would you suspect with the double bond, would you have a bigger balloon or a smaller balloon or the same size balloon? As far as repulsions go, as far as the space that's required. You'd have a bigger balloon. So a double bond would be bigger, not twice as big, but bigger. Triple bond would be bigger, it takes more space. So this is just showing a linear EPG, linear EPG with balloons. If we've got three balloons, we'll have trigonal planar EPG, angles 120. This is a tetrahedral EPG, angle 109.5. It's rounded actually to 4 6 109.5. So these are the scenarios for the shapes that we have. We have the EPG shape. This is the EPG shape. This is the MG shape. The MG shape MG stands for molecular geometry. So there are two geometries. There's the EPG, which is electron pair geometry, and the MG, which is molecular geometry. The EPG just shows us the shape of the groups of electrons. Because of the Heisenberg uncertainty, for example, if we only have, let's say we have 4 groups of electrons, it's tetrahedral, but if we only have 3 bonds, 3 single bonds and 1 lone pair, that lone pair is shown here. Well, we don't really pinpoint that lone pair, so the atoms can be pinpointed or determined where the position is. So when we look at the atoms, the shape of the bonded atoms that results, this is the MG. And so the EPG is the shape of the groups of electrons, the MG is the shapes of the atoms, the shapes that the atoms make. And sometimes they're the same, sometimes they're different. And so we'll just run through these quickly here. Then we'll do some examples. So for example, if I have 2 groups, then the EPG should be linear, that is 180. Now if I have, let's say, 2 single bonds, that is an ABA type molecule, then the MG is also going to be linear. So the MG matches the EPG if I look at the atoms. So this is the space filling model. This is where we can show how things are linked together. This would be like BEF2. BEF2, even though it's a metal and non-metal, forms a molecular compound, not an ionic compound that you'd expect. We go on to this one. If we have 3 groups, when we have 3 groups of electrons, we're always going to have the trigonal planar EPG. This, so the 3 groups. Now, depending on what those groups are, so for example, if I have 3 single bonds here bonded to A, atom A, this will be like BF3, then the EPG and the MG are the same. The EPG is trigonal planar, the MG is trigonal planar. This is the space filling, what it looks like over here. This is Lewis structure. However, if I have 2 bonded atoms and 1 lone pair, like in this case, I have 2 bonded atoms, like in SO2. I have a double bond here, a single bond here. That would be, well, look at this. This would be the what we call angular or bent. But we have 2 angulars of bent. This is angular bent of 120. So the lone pair is here, but I'm going to draw it. It's stuck on the bottom here. If you look at the atoms themselves, it's just kinked. It's bent. We've got 4 groups. We'll have tetrahedral. It's tetrahedral 109.5. We have 4 bonded atoms. It's going to be like in methane. It's going to be a tetrahedral MG as well. In ammonia, it's different. In ammonia, we have 3 bonded atoms and 1 lone pair. And so 3 bonded atoms and 1 lone pair, the EPG is the same. We've got 4 groups. So 3 bonded, 1 lone pair. But when we look at the MG, we're just looking at the atoms themselves. When we look at the atoms themselves, it's going to adopt this This is called trigonal pyramidal. There's a lone pair that's stuck out there. If we look at tetrahedral here, in this case, where we have 2 bonded atoms and 2 lone pairs, like in water. Water has 2 bonded atoms, 2 lone pairs. It's going to look like this. The Lewis structure, you see the Lewis structure doesn't have to show the actual shape. I mean, this Lewis structure looks like a T, but the actual shape of the molecule is this trigonal pyramidal. Here, the Lewis structure, yeah, looks like a 180, this looks like a 90. It's neither. It's 109.5. It's bent. 109.5. So what we're going to do is we're going to try to draw these as accurately as possible. So something like BEF2 is pretty straightforward to draw. BEF2 is like this. BEF2. The ETG, we'll say, is linear, which sets the angle. You know, linear should be a 180-degree angle. And the MG is linear. It's the same, 180 degree. Now, when we do the 180 degrees, this is called the bond angle. And to get more specific, for the bond angles are defined by 3 atoms. And so what we'd say is this is the FBF angle. The FBF angle is 180 degrees. Equals 180. Okay, let's go on to SO2, which is or no, BF3. BF3 next. It's not greater, it's just the angle.
Oh, it's just the angle.
Yeah. So it's like this with the line.
So like in chemistry, that's like angle.
Yeah, this is angle. And so the way I read it is FBF angle equals the 180 degrees. So it's a symbol for angle. They do in BF3. They do in BF3 like this. It doesn't matter how you do it. I'm going to flip it the other way, so I do it like this. So when we look at this, when we do the EPG and the MG, this is the way I look at it. When I do the EPG, I look at the electron groups, 2 single bonds. So that's the EPG. When I do the MG, I look at the atoms. So these are the atoms. The atoms, the green matches the red. So it's the same. And so again, I'll do the EPG. I just look at the groups of electrons. 3 groups of electrons. 3 groups of electrons tells me that I have a trigonal planar EPG. 3 groups. 3 groups equals trigonal planar. Planar is spelled P-L-A-N-A-R. Planar. That's the EPG. Then I look at the bonded atoms. The bonded atoms are the same arrangement. And so the MG here is also trigonal planar. And the angles we are going to get next. It's going to be the FBF angle. FBF angle. And what is the FBF angle? Yeah, 120 degrees. The FBF angle. Okay, we're going to look at the next example that they did, SO2. SO2, like this. There's a lone pair, a double bond, and a single bond. A couple of things I should mention. Note, double bonds, what do you think? Are double bonds shorter, longer, or the same length as single bonds? They're shorter. Okay. Now, if double bonds are shorter, are they stronger, weaker, or the same strength? Stronger, shorter and stronger than single bonds. And so, one thing for this structure, what are the formal charges in this particular structure for SO2? And oxygen? Negative. Now, in this slide, I just copied. They made the double bond on the left, but we could have just as easily made the double bond on the right. If I make the double bond on the right, then I get this structure here. So in this particular structure, this is neutral, so I don't need the square brackets. The plus and the minus cancel each other out. I can't get rid of that. Actually, I could get rid of that. You know how I could get rid of it? By another double bond. But that would require doing what to sulfur? It would require expanding its octet. And so this is an octet with formal charges. We're just going to leave it like this right now. These are two resonance forms. So what's happening with resonance? So for example, does it say 5 seconds in this form and then the next 5 seconds to this form, so it just switches back and forth? Or is it resonating much faster, maybe 1 second here, 1 second here? Or maybe much faster, maybe 1 microsecond here, 1 microsecond here? And so what's happening is when people think of resonance forms, they think of something resonating, vibrating, some kind of frequency. And so they're thinking of this as vibrating back and forth, back and forth, back and forth. So what's happening is this bond, short, long. And what's happening with negative charge? Negative charge here, negative charge there, negative charge here, negative charge there. So the negative charge is flipping back and forth. And the bonds are doing this, and the charge is doing that. And so a lot of people think that that's what's happening. But it turns out it's not what's happening. The true structure of this is called the hybrid. It turns out that when people measure the bond lengths here and the bond energies, it turns out these two bonds are exactly the same. And so experimental evidence shows the two bonds are equivalent. Two bonds are the same. And so neither one of these is accurate. And so what people have come up with is this kind of add-on. We're going to do an add-on thing. And that's called the resonance hybrid.
What's that first word you have?
Okay, experimental evidence shows the two bonds are the same. The two bonds are identical. And so, more accurate structure is the hybrid. The hybrid is just the average of all resonance forms. resonance form structures. Whatever. And so rather than having a double and a single and a single and a double, in the hybrid, what they have is they have 1.5 bond each oxygen. So this is a 1.5 bond. The sulfur is going to maintain that positive formal charge. Each oxygen is going to have 2 lone pairs fixed on it, and then 1 lone pair that's going to be spread out, smeared out. And so the way that one could think about this is it's like this. Let's say you had a bathtub, a V-shaped bathtub like this. And let's say you put 2 feet of water here and 1 foot of water here. If you had a barrier here that prevented the electron cloud from, or prevented the water from moving, you can maintain this. You could put 1 foot of water on the right side and 2 feet of water on the left side if you had a barrier here. And so we call this localization. We could localize 2 feet of water on the left and 1 foot of water on the right. But what happens in resonance forms is the electrons can be delocalized. One way to visualize how the electrons can be delocalized is like this. Let's say that lone pair pops in here and then that kicks out of one of the bonding pairs. And so what can happen is electrons can redistribute themselves, electron cloud, and we convert to this form. Or we can go back to that original form. Let's drop this lone pair in here and then kick out this pair out here, and then we're back to the original form over there. And so what's happening is there's nothing preventing the electron cloud from spreading out. The electron cloud's just going to spread out like water or fog. And so what's going to happen is this is not sustainable because there is no localization. The electrons can be delocalized like this. In other words, what's going to happen is it's going to spread out, and we can't sustain this localization. And what we're going to end up with is a situation where both sides are equivalent, and they're going to be 1.5 feet on both sides. So this is what's happening with the electron cloud here. The double bonding electrons are being spread out. The cloud is being spread out over 2 bonds. So each bond comes out with 1.5 bond. And then this lone pair that seems to go back and forth, that's going to be spread out over both. And so when that happens, then the end result is we get a -1 charge distributed over 2 atoms. -1 charge distributed over 2 atoms gives us -1/2 formal charge. So we have -1/2, -1/2, and plus gives us 0. So this is the hybrid structure. But regardless, whether we look at the hybrid structure or we look at one of these, the easiest thing to do when we're doing VSEPR is just pick one. We'll pick the left one or the right one. Just pick one. That'll make our life a little bit easier. And so we'll build this one. Or we can take the hybrid structure. In this sense, we get the pairs. It doesn't matter what the pairs are. If I look at this and count how many groups of electrons do I have, they're all the same. So for example, here I have a lone pair, that's one group. I have a single bond, that's another group, and I have a double bond. I can't split the double bond into 2 separate groups. It has to be taken as a whole. It's not, one double bond does not equal 2 single bonds. One double bond is a double bond. That's it. And so how many groups of electrons do I have here? I have 3 groups. Just lone pair, double bond, and a single bond. That's 3 groups of electrons. What's the geometry? Well, the geometry is just the atoms. So when I look at the geometry, the MG is different. The EPG, which is the red, is trigonal planar, but when we look at the MG, which is the green, does that look trigonal planar? No, it looks bent. And so this is called bent at 120. okay, it's the same thing here. You know, when I look at the EPG, I got 3 groups. Lone pair, single bond, double bond, that's 3 groups. So the EPG is trigonal planar. The MG again is the same. It's going to be bent at 120. If I look at the hybrid's going to show me the same kind of thing. The hybrid shows 3 groups. You know, lone pair here, a 1.5 bond here, a 1.5 bond here. I don't split that. And so the EPG is trigonal planar, and the MG again is angular or bent. Here. MG. So we're going to go to the next molecule here, which is going to be methane. Now methane, the way we draw it is like this. We need to know how to draw a tetrahedral orientation of groups. So these are all single bonds, so let's do that. So we put 2 in the plane of the page at 109.5 angle. And then one's going to stick out as a wedge, and another's going to stick in as a dash. So we end up with a tetrahedral configuration like this. It's kind of like a tripod. You have a tripod here, and then one's stuck on the top.
So the dash is behind
Yeah, the dash is going behind the board into the board. Let's see. Grab my tetrahedral.
That's like a so the dash is behind.
Somebody has the tetrahedral, so I'll show it to you. Anyway, practice drawing this. Can you draw it just like this? If you could draw it just like this, then there won't be any problems. Won't be any problems. All right, so methane has just hydrogens attached here, like that. And so the EPG's tetrahedral, I have a tetrahedral arrangement of single bonds like this. Just show them as little balloons. Yeah. Tetrahedral arrangement of balloons. And when I look at the atoms, it's the same. You know, I have a tetrahedral arrangement of the atoms too. And so we'll say the MG, or actually first we start off with the EPG. EPG is tetrahedral. It's going to set the angle, it's 109.5 degrees. I forgot to write the angle over here, didn't I? Let me complete this. Let me complete the previous. The EPG is trigonal planar in the previous problem. Trigonal planar, that sets the angle at 120. And then the MG is, what did we say, bent? Bent is easier to write than angular, so I'm going to call it bent. And then the angle is going to be the OSO angle. When we do the angles, I don't show double bond or 1.5 bonds. I just show the links. The O linked to the S, linked to the O. The OSO angle is going to be what? 120 degrees. Going over to methane, the EPG is tetrahedral. The MG is tetrahedral, the same. Tetrahedral.
How do you know when to draw the columns? Like the dash is smaller?
How do you know when to draw the dash and
Or
the?
like, why can't it just feel like how they have it there?
Why can't it be how they have it here? Don't draw as they have it.
No, not that one, you know. Like 4 lines around it, the
This one?
Yeah.
The Lewis, because the Lewis shows 90-degree angles, it's not accurate. Lewis diagrams don't have to be accurate. If somebody asks you to draw a Lewis diagram, they don't care. If somebody asks you to draw the shape of the molecule, then they care. And so when we do the Lewis diagram, it's too much to worry about the shape. Just draw it out.
Maybe the angle at the bottom, does it matter the order that we put it in, or is it always gonna be like the outside?
It does matter the order, so sometimes what we'll do is we'll label it. You know, oxygen 1, oxygen 2, that kind of thing. We'll see. I'll show you. But in this case, there's only one angle. There's only one angle. The OSO angle is going to be 120. Over here, there are multiple angles. You know, we have this H, this C, this H. It's 109.5. This H, this C, this H. 109.5. There, here, here, back here. They're all 109.5. There's multiple angles here, but they're all the same. So what we'll just say is that the H, C, H angle, regardless of which ones you pick, are all the same. They're going to be 109.5 degrees. Now, we might tweak the orientation of this a little bit. You'll see. But as long as you can draw the basic shape like this, then you're good. Because you can figure out, you know, if we twist it, what's going to happen. You just want that reference. It's always going to be two in the plane, one coming out, one going in type arrangement. Let's go on to the next. The next molecule is going to be ammonia, NH3. This is the way I'm going to draw it. They're going to be how many groups? If I do the Lewis structure, I don't care about the shape. I'll draw it like that. But when I look at that, how many groups are there? Well, I have a lone pair, that's 1. I have a single bond 2, single bond 3, single bond 4. 4 groups. If I have 4 balloons, how should I arrange those? It's got to be a tetrahedral arrangement. And so I'm going to have a tetrahedral arrangement of groups. Now, what I'm going to do is I'm going to put the, I'm going to draw it like this. I'm going to put the lone pair in the plane like this, and one of the bonds in the plane like this. That means one of the bonds is going to stick out, and another bond is going to stick in like this. So I'm going to draw it like that. It's going to be, and so it's going to be like this. If you're trying to visualize it, the pens, be something like this. This is trigonal pyramidal. The shape. Now, I look at the arrangement of balloons, it's got this trigonal pyramidal shape, but when I look at the arrangement of the atoms, or tetrahedral shape, sorry, when I look at the arrangement of the atoms, it's got a trigonal pyramidal shape. So this is what we're going to say, is the EPG is going to be, electron pair geometry is going to be tetrahedral, and that's going to set the angle at 109.5 degrees. But the MG is going to be trigonal. It's a pyramid with a triangle base, so I'm going to call it trigonal pyramidal. And then we have the H and H angle. The H and H angle should be what? 109.5 degrees. Now, we're going to talk about this briefly. I'm going to talk about distortions to the angle. What happens is these groups take up different amounts of space. And so it turns out that, let's say I have the atom with a lone pair. A lone pair takes up a lot of space compared to a single bonded pair. Because if I have an A bonded to a B, what happens is B tries to pull off some of the electron density from A. And so there becomes a tug of war. Here, that lone pair belongs only to A. Here, there's a tug of war for the electron density. And so B tries to pull off the electrons away from A. Like that. And so it turns out that a lone pair occupies more space than a single bond. A double bond, a double bond is going to occupy, double bonds are shorter. So double bonds occupy a lot of space too, like a lone pair. So the bigger the balloon, the more space it requires. And so what happens here is this lone pair is a big balloon here, whereas these single bonds are smaller balloons. And so that big balloon means that it's going to have more repulsions down here. And so what it does is it pushes these down. As these get pushed down, it compresses the angle here. And so for a lone pair, it's about a 2-degree distortion. So the angle's about 107 degrees. About 107 degrees distorted. About 107.5. About a 2-degree distortion. Good question. How did I get the 107? This is how I got the 107. I got the angle from experimental data. You know, this is what we're predicting, but the actual bond angle is 107.8. Do you see that? This is the actual angle measured experiment. And so I should just say about 107.5. We'll just say about a 2-degree compression of the angle, distorted. It's because the lone pair is a bigger balloon, greater repulsions. This is a bonding pair. Bonding pair is tug of war between two atoms, so it's being pulled. No electrons out. Okay, now we're going to go to water. So the general, this is kind of an empirical, very qualitative empirical. Very qualitative empirical, each lone pair results in about a 2-degree compression of the bond angle. So now we're going to go to the H2O. H2O, when I draw out the Lewis structure, tell me what is the angle here? Well, that angle looks like 90 degrees, doesn't it? Or I draw like this. This angle looks like 180 degrees. Neither is accurate because Lewis structures don't need to be accurate. So what we're going to do is we're going to try to draw its 3-dimensional shape. When we do that, we've got to count how many groups of electrons. So we've got a single bond group, a lone pair group, and a lone pair group. How many groups is that? That's 4 groups. So the electron pair geometry is going to be tetrahedral. Now for tetrahedral, the easiest thing for oxygen is I like to draw the bonds in the plane if possible, except for ammonia, I didn't do that. So I'm going to draw the two bonds in the plane like this, and then that means one lone pair sticks out. And so we'll make it bold. And then another lone pair sticks in, and we'll make it dotted. And so I have three ways that I draw lone pairs. If I draw circles like this, it's in the plane of the page. If I blacken out those circles like this, it's sticking out. If they're dotted, it's sticking in. And so this is the way I visualize this. Okay, I have one group in the plane, another group in the plane. These two groups are the plane. And then I have this group sticking out the plane, and then this group sticking into the plane. And so this gives me my tetrahedral EPG. And so the EPG is what we call tetrahedral, and that's going to set the angle. The angle should be 109.5 degrees. However, when we go to the MG, what does the MG look like to you? The MG is just the geometry of the bonded atoms. When I look at the geometry of the bonded atoms, what does it look like? It looks like it's bent, yeah. And so the MG is bent, but this bent is different than the last bent because this bent has a different angle. This bent is not 120, this is bent at 109.5 degrees. And so we have the HOH angle. The HOH angle should be 109.5 degrees. But there's potential for distortion because the lone pairs are bigger balloons. And so we got two big balloons here pushing down on these two littler balloons. So the two little balloons are going to be compressed in. And if they're compressed in like this, then that's going to shorten this angle by, it's about 2 degrees per lone pair. And so we're going to go from 109.5 to 107.5 because of this lone pair. And then we're going to go from 107.5 to 105.5 because of this second lone pair. So the two lone pairs are going to result in a 4-degree compression. And so what we'll just say is distorted, it's going to be about what? One 107 would it be if we had one lone pair, but we got two, so it's going to be close to 105. And so the distorted angle is about, this is just a guess, 105.5 degrees. What is the actual angle in water? And so let's take a look at the actual angle. The actual angle in water is 104.5. So we're off a little bit, but we're just guesstimating anyway. So do you see? This is a guesstimate.
You know where you put the other lone pair? Is the dash one? Is that behind?
Yeah, that's behind.
So it has 3 legs, 4 legs.
Yeah, well, it has
So
3.
It's not a bond, so does it stick out? Or does
Yeah, it sticks out.
the lone pairs stick out?
Yeah, lone pairs are going to stick out. And so they're still there. It's like we still have 4 balloons. They're just different sizes. These balloons are bigger. These balloons are smaller here. And so if we're looking at the balloons, the lone pairs are going to be like this, whereas the bonding pairs will be like that. So these lone pairs kind of push or bully these bonding pairs closer to one another. It's not really shown here. You can see the lone pairs. You see the lone pairs of these two big balloons here. It's going to compress the angle here. That's what they're trying to show here. This is showing the tetrahedron. Tetrahedrons are 4-sided polygons. And so if you connect all the hydrogen atoms, the lone pairs here, we'll get a 4-sided polygon. But when we look at the molecular geometry, this is what we see in molecular geometry, the bonded angles, the HOH is what we see. So water molecule looks bent or angular. These are all showing the tetrahedral EPG, 4 group. Here we have actually 4 bonds. Here we have 3 bonds and 1 lone pair. Here we have 2 bonds and 2 lone pairs. They're all tetrahedral EPG because they all have 4 groups. So the MG is different. This is a tetrahedral MG. The HC, H angles 109.5. This is a trigonal planar, or no, it's not trigonal planar. This is trigonal pyramidal. And the H and H angle is 109.5 or distorted about 107. This is bent. The HOH angles 109.5 or distorted about 105. Those are these molecules here. So try this one. We're going to try nitrogen trichloride. We call these the wedge dash diagram. It's a 3-dimensional shape of these. So try that. First thing is we need the Lewis structure for this. All right, the steps involved. Step 1, how many groups of electrons? 4 groups. And so this is, I'll just break it down into steps. Step 1, number of groups. Number of groups is going to tell us the EPG. So if we have 2 groups, what is the EPG? Linear. If we have 3 groups, what is the EPG? Trigonal planar. If we have 4 groups, then we look at the number of bonded atoms, you know. And number of lone pairs. So looking typically with linear, we just have 2 bonded atoms. Number of bonded atoms. Number of lone pairs. And so typically we have 2 bonded atoms. That gives us linear MG. For trigonal planar, we have 2 scenarios that come up here. We have 3 bonded atoms. 3 bonded atoms. That gives us trigonal planar. Or we have 2 bonded atoms, 1 lone pair. 2 bonded atoms, 1 lone pair. This gives us bent at 120. And for tetrahedral, we have 3 scenarios that come up. We have 4 bonded atoms, 0 lone pairs. 4 bonded will give us tetrahedral. Then we have 3 bonded, 1 lone pair. Which gives us trigonal pyramidal. two bonded with two lone pairs, which gives us bent, but this bent is going to be at 109.5. This is over here. This is 180. Linear, trigonal planar is 120. Tetrahedral is 109.5 degrees. Just kind of remember. And so we could see what scenario we're here. How many groups? 4 groups. 4 groups, we have tetrahedral EPG. And then we see how many bonded atoms do we have? 3 bonded, 1 lone pair. This is going to give us a trigonal pyramidal, Mg. Now, with trigonal pyramidal, I like to draw trigonal pyramidals the same way. For a trigonal pyramidal, this is what I like to do, is I like to put the lone pair in the plane page. And then how do I draw the bonds?
One single bond.
Okay, to the side here in the plane, and then, yeah, and how should I draw? Yeah, well, first I'll draw the wedge, good. And then I'll draw the dash, because the dash actually goes behind the wedge over here. So I have it like that. So that would be the trigonal pyramidal. We'll take a break now and then start up again.